Welcome to the Silent Architect. Today, we are undertaking a deep forensic dive into the most revolutionary piece of technology of the last decade, the transformer. This architecture is not just the backbone of every modern large language model, from ChatGPT to Claude, but it is fundamentally changing how humanity interacts with information, generates creativity, and processes data. These systems are silent because they operate deep within massive data centers, processing billions of data points without noise, yet they are the ultimate architects, building sentences, code, and ideas on a scale previously unimaginable. Our journey today is the anatomy lesson of this silent, powerful force. We will pull back the curtain, examining the core components and the ingenious mechanisms that allow these models to understand context, handle immense scale, and generate human-quality text. If you want to understand the true core of modern artificial intelligence, this journey into the heart of the transformer begins now. In recent years, a seismic shift has occurred in the world of artificial intelligence. A new class of models, exemplified by systems like ChatGPT, has emerged from the digital shadows, proving capable of generating complex, coherent text that is often indistinguishable from human output. These systems operate on an immense scale, achieving capabilities that were simply thought impossible just a few years ago. Our investigation begins with the fundamental question: what enabled this leap? To appreciate the transformer's genius, we must first look at the old guard. Prior to this revolution, AI heavily relied on recurrent neural networks, or RNNs. The problem with RNNs was their sequential, forgetful nature. They had to process information one piece at a time, like reading a scroll line by line, constantly struggling to remember context from the start of a long text. This sequential bottleneck meant RNNs simply couldn't be scaled efficiently enough to handle the massive datasets required for achieving the current state-of-the-art performance. The new power needed a new blueprint, one built for speed and immense data, and that blueprint is what we will explore next. The breakthrough moment arrived in 2017 with the landmark paper titled "Attention is All You Need." This paper didn't just propose a new model, it unveiled the transformer architecture, which ruthlessly abandoned the complex, sequential, and slow recurrent structures of the past. The transformer's power rests solely on one ingenious mechanism: attention. It removed the need for recurrence entirely. Now, what makes this shift so foundational? The critical advantage of the transformer, highlighted in the key insight on the right, is its inherent ability to be highly parallelized. Think back to those old RNNs that had to read one word after the next, slowing down training considerably. The transformer, however, processes all tokens in a sequence simultaneously, in parallel. This massive architectural shift is what allows us to train these models on truly gargantuan datasets across thousands of specialized processors. Without this ability to parallelize computation during training, the era of ChatGPT and sophisticated large language models would simply not exist. This decisive move from sequence dependence to parallel computation is the first and most critical key insight into the transformer's success. If you crack open a large language model, such as any model in the GPT series, you will find a surprisingly modular and elegant design. The entire network is constructed by simply stacking one fundamental component on top of another, over and over again. This core repeating component is known as the transformer block. At the base of the entire stack is the input layer. This is where we feed in our initial data through token and position embedding, ensuring the model understands both what the word means and where it sits in the sentence. At the top of the stack is the output layer, typically a linear layer followed by softmax, which provides the final probabilities for the next predicted word, allowing the model to choose its output. Sandwiched between the input and output is the operational core, a number, denoted by n, of identical transformer blocks. This stacking mechanism is crucial because it allows the model to progressively refine its understanding of the text. Early layers might capture simple relationships, while deeper layers can encode highly abstract, complex semantic meanings, enabling the model to effectively reason and generate highly sophisticated text. Let's take a closer look inside this fundamental unit, the transformer block, which is the operational heart of the entire network. While the overall purpose of the block is to process and refine the data, it relies on several key elements to maintain stability and enable deep learning. we see two crucial mechanisms: skip connections, labeled as add, and layer normalization, labeled as norm. The skip connection is a critical highway that allows the input information to bypass the block's main processing path. This is vital in preventing the signal from degrading or vanishing as it passes through the many layers of a very deep network. Layer normalization, or norm, stabilizes the entire training process. By normalizing the data at each step, it ensures that the values don't become too large or too small, leading to faster and more reliable convergence during training. These two components provide the stability necessary for scaling. However, the true analytical core, the powerful engine of the transformer block, is the multi-head attention layer. This is where the magic truly happens. This is the component that learns to weigh the relative importance of every single word in the sequence dynamically. It is the core innovation that gives the transformer its immense contextual power, and we must investigate it further. The core attention mechanism doesn't just learn one way to connect words, it learns many different ways, simultaneously. This is the concept behind multi-head attention. Instead of running a single, unified attention mechanism, the input is split and processed by multiple independent attention heads in parallel. Each head operates independently, learning a distinct, specialized type of relationship within the text. For example, one head might specialize in tracking grammatical dependencies, correctly connecting verbs to their subjects regardless of distance. Another head might focus exclusively on thematic connections, linking concepts that are semantically related, like dog and leash. A third head could track pronoun resolution, connecting she back to heiress. Each head takes the input and calculates its own query, key, and value vectors. The outputs from all these specialized heads are then concatenated back together and projected into a single, cohesive final vector using a linear layer. This projection allows the entire layer to integrate these diverse findings, learning far more complex and nuanced relationships than any single, isolated attention mechanism could ever hope to achieve. This parallelism gives the transformer its unparalleled power of comprehensive contextual understanding. The core secret behind the transformer's ability to generate coherent and contextual text is that it completely prioritizes relevance over linear sequence. The traditional constraint of textual distance is broken. When the model chooses the next word, it doesn't just look at the word immediately preceding it. It dynamically pays attention to the most important parts of the entire context, regardless of how far back they appear in the input sequence. Consider our sentence example. The PI watched the heiress enter the smoky nightclub, but the thing he couldn't forget was the blank. To predict the next word, which might be scar or name, the attention mechanism dynamically knows that the query for the blank word is highly relevant to PI and possibly heiress, because they are the main characters of the narrative. Critically, it correctly identifies that descriptive but peripheral words like smoky or nightclub are likely irrelevant to the specific action. Attention is a sophisticated mechanism that allows the model to dynamically decide which parts of the input to focus on, weighing their importance to the current task. It can pull crucial information from anywhere in the context without being clouded by irrelevant details, which is exactly why LLMs exhibit such long-range coherence and deep understanding. To execute this dynamic relevance weighing, the attention mechanism uses three key vectors, often called the forensic tools: query, key, and value, or Q, K, and V. Think of the entire process as an extremely efficient information retrieval system operating within the brain of the AI. First, the query, or Q, represents the current task or search criterion. For the word we are trying to predict, the query asks a question, such as, what kind of word should follow the phrase was the? Second, the key, or K, is a representation of what each word in the existing sentence can offer. It acts like a label or index describing that word's potential relevance to the current query. Third, the value, or V, is the actual content or semantic contribution of the word. The process begins by matching the query and all the keys using a dot product, which produces the attention score. This score is then normalized using softmax to create the weights, which are probabilities indicating relevance. Finally, these weights are multiplied by the corresponding value vectors, creating weighted values. Summing all these weighted values gives us the final context vector, which is the rich, relevant information the model needs to finalize its prediction. While the attention mechanism is powerful in identifying relevance, it has a fundamental weakness. On its own, it is permutation invariant. This means it treats a sentence as a simple bag of words and doesn't inherently care about word order. This is a massive problem in language, as order determines meaning. Consider the critical difference between the sentences: the detective shot the informant and the informant shot the detective. They contain the exact same words, but their meanings are entirely different. The transformer needs a city map, a way to explicitly encode position. The solution is positional encoding, specifically positional embedding. Before the text enters the first transformer block, each word's initial embedding, which represents its meaning, is combined with a special positional embedding, which represents its location in the sequence. The mechanism is straightforward but brilliant. A unique vector representing the position, such as first, second, third, and so on, is mathematically added to the unique vector representing the word token. This creates a final input encoding vector that captures both what the word is and exactly where it is located relative to the other words, resolving the core challenge of maintaining grammatical and syntactic structure without resorting to slow sequential processing. For a text generation model, specifically a decoder transformer like those in the GPT series, the primary task is generation, predicting the next word given all the previous words. If, during the training phase, the model were allowed to see the entire completed sentence it was supposed to be generating, it would simply copy the correct next token, trivially solving the task and rendering the training useless for genuine generation. We must enforce the fundamental rule of causality: no peeking into the future. The solution is causal masking. This critical step involves applying a triangular mask during the attention calculation. This mask explicitly forbids any given position from attending to or gathering information from positions that come after it in the sequence. Look at the grid on the screen. The cells marked with X represent the masked, inaccessible future tokens. If the model is currently predicting word 5, it is causally masked, meaning it can only use information from words 1 through 4 to inform its decision. This masking ensures that the decoder is forced to rely only on the context it has already processed, thereby guaranteeing that it learns the necessary skills to genuinely predict and generate the next word sequentially and reliably. One of the most powerful and useful aspects of the transformer is its interpretability. Unlike many complex neural networks, we don't have to treat it as a complete black box. We can actually inspect the attention scores to visualize what the model is thinking and where it is sourcing its information for a prediction. Let's analyze a phrase generated by a model trained on a corpus of classic noir detective novels. The phrase ends with, "The city slept, but for one lone detective, the case file on his desk held the final." When the model is preparing to predict the next word, which we anticipate will be something specific to the genre like clue, piece, or secret, we trace back to see which preceding words it pays the highest attention to. The visualization clearly shows the model dedicating high attention scores to the critical context words: detective, case file, and the preceding word final. Crucially, it correctly downweights irrelevant descriptive words like city or slept. By concentrating its analytical power on the narrative anchors, the detective and the case file, the model grounds its prediction in the core theme of the sentence, demonstrating a sophisticated understanding of context and narrative necessity. This ability to visualize relevance is invaluable for understanding, controlling, and debugging complex AI systems. The core transformer blueprint is highly flexible, allowing it to be configured in 3 primary architectural factions, each suited for different types of tasks. First, we have the encoder-only models, which we call the interrogators, exemplified by BERT. These models read the entire text input at once, using bidirectional attention, meaning every word can see every other word in the sequence. Because there is no causal mask, they create a rich, complete contextual understanding, making them perfect for tasks that require deep comprehension, such as sentence classification, named entity recognition, and extractive question answering. Second are the decoder-only models, the oracles, such as the models in the GPT series. They are specifically designed for generation. They use unidirectional attention combined with the causal mask we discussed, meaning they can only look at the past, generating text one token at a time. Their key use cases center around creative text generation, powering chatbots, and summarization. Finally, we have the encoder-decoder models, the translators, like T5. These models map an entire input sequence to a corresponding output sequence, making them the standard, powerful choice for tasks like machine translation, complex abstractive summarization, and question answering, where both robust context input and sequential output are necessary. To understand how complex, sequence-to-sequence tasks like machine translation are achieved, we must examine the encoder-decoder model, the ultimate anatomy of a translator. This architecture consists of two distinct, stacked components linked by what we call the bridge. The process starts with the encoder stack. The encoder reads the source sentence, such as English. Its self-attention layers are completely unmasked, allowing every single word to see every other word in the input, building a thorough and bidirectional representation of the source meaning. This complete contextual embedding is then passed to the decoder. The decoder's job is to generate the target sentence, for example German, one word at a time. It uses two attention mechanisms at every step. The masked self-attention, which we know maintains causality, looks only at the words the decoder has already successfully generated in the target sentence. Crucially, the cross-attention forms the bridge. This layer looks at the final output of the encoder. It is how the decoder knows what meaning the translation needs to convey, connecting the generated target words back to the source language's full context, ensuring semantic fidelity and acting as the vital link between the two languages. While the transformer architecture provided the necessary blueprint, the dramatic rise of the AI empire has been fundamentally driven by the sheer power of scale. The underlying architecture of the foundational models has remained remarkably consistent, but the key driver of improvement has been an exponential increase in two critical factors: the model size, measured in the number of parameters, and the volume of training data used. Look at the timeline displayed. GPT in 2018 had 117 million parameters. By 2019, GPT-2 soared to 1.5 billion parameters. And by 2020, GPT-3 reached a staggering 175 billion parameters, alongside a massive context window capable of handling thousands of tokens. This explosive scaling doesn't just make the models incrementally better. It unlocks what researchers call emergent abilities. Highly complex skills, such as few-shot learning and sophisticated abstract reasoning, were not explicitly programmed into the system by engineers. Instead, they spontaneously emerged from the immense scale of the model and the vastness of the data. This trend continues relentlessly, with the latest models, like GPT-4, evolving into multimodal systems, capable of seamlessly processing and understanding not just text, but also images and complex graphical inputs. A raw large language model, having ingested trillions of words, is simply a prediction machine. It knows how to predict the next word beautifully, but it doesn't inherently know how to be helpful, safe, or follow complex human instructions in a useful way. The final, crucial step in creating modern conversational AI is a fine-tuning process known as reinforcement learning from human feedback, or RLHF. This is the intricate process that aligns the model with complex human intent and values. The RLHF pipeline has 3 stages. First is supervised fine-tuning. Human labelers create a high-quality dataset of ideal, appropriate conversations to initially tune the base model, giving it a baseline understanding of desirable behavior. Second is reward modeling. Humans rank several of the model's responses to a given prompt from best to worst. This ranking data is used to train a separate, smaller reward model, which is essentially a powerful predictor of human preference. Finally, we have reinforcement learning. The language model generates responses, the reward model scores them based on the predicted human preference, and an RL algorithm, typically proximal policy optimization, or PPO, updates the language model's weights to maximize this predicted human preference score. This rigorous final alignment process is what teaches the silent architect not just to construct language, but to communicate with purpose, safety, and helpfulness, completing the entire anatomy of a modern conversational AI.